Hi, I am Lance Dagohay, a BS Physics student from Ateneo de Manila University. I will be presenting to you our paper on coming up with a low-cost, low-complexity electronic analog of the phenomenon known as the relativistic aberration of light using op-amp-based all-pass filter circuits. The idea is simple. We want to bridge special relativity in engineering. Previously, the team used PICs and optical thin films to address this idea. However, we encountered some problems. 1. These technologies are too expensive. 2. They are not easily accessible. And 3. They are complicated to set up. Now the question is there a cheaper, more accessible technology that we can use to perform analogs of special relativity? The answer is yes, and that is what we did on this paper. Here we proposed an electronic circuit analog of the relativistic aberration of light, or RAL, so we can study it in a more convenient space. To establish this analog, we went through 2 stages. First, we developed an analytical model from the equations describing RAL so that we can identify our circuit design and our parameters. Physically, this means translating this theoretical idea of RAL into a first-order APF circuit. Second, we simulated this idea using LT-SPICE and electronic circuit simulation software. The plots we got are characterized by a Z-shaped profile as shown in figure 3b. We take note 3 important points: 1 Hz, 10 Hz, and 1 kHz, where the phase response is around 0 degrees, 180 degrees, and 360 degrees respectively. Lastly, we set up an experiment in an electronic laboratory. We ran trials for the 3 frequency points mentioned before, and we see that the phase shift generated from these points are very close to our simulation results. Hence, we can verify that the parameters of this analog is true given the boundaries of this trial. To summarize, we offered a solution to our problem earlier by presenting an electronic analog of RAL. We chose this because it is cheaper compared to other approaches, the circuit design is simple, and the materials can be found in a typical engineering laboratory. The experiment as a whole is accessible to anyone who would like to recreate it. In general, we believe that it is good to consider this method to make learning more digestible to students and accessible to those with limited facilities. Thank you, and that's it for my talk. Thank you for listening.
In this study, we constructed a multi-radio wireless sensor network equipped with a sensor and at most 2 radio transceivers to gather temperature and relative humidity data in a building. Sources and sinks of heat and moisture can be detected using this instrumentation while having 73 to 100% success rate. To monitor large environments, data from numerous points should be collected. This can be made easier with wireless sensor network, where multiple devices called wireless sensors or nodes can gather, process, and store data, as well as to communicate with other wireless sensors such that all gathered data can be compiled in a special device called base station. A study has shown that using 2 radios with different characteristics can improve communication in WSN. We employed this fact in creating multi-radio wireless sensor network to monitor temperature and humidity in a building, with results can be used in monitoring other large environments and improving the network. To create a multi-radio wireless sensor network, the nodes were constructed first using 80MHz microcontroller, the HD11 sensor, and transceivers NRF2L01 and or LoRa32 with ESP32 microcontroller. The network was used to monitor ambient temperature and relative humidity inside research wing of National Institute of Physics every minute for 90 minutes. For the performance of WSN, transmission success as high as 100% and as low as 73% were recorded, affected by nearness of nodes to base and the availability of nodes. In monitoring the environment, recorded data exhibited difference of parameters even though 2 sensors were within the same room and only meters apart. Lower temperature and humidity were recorded in Node 1 compared to Node 3 due to its proximity to an air conditioner, while in Node 7, higher RHs were detected than Node 9 due to the presence of water dispensers and sinks. Increasing RH was also registered by Node 6 due to the occurrence of sunset. This showed that even a smaller environment such as a room can have temperature and moisture distribution, and this can be monitored by WSN, especially when the number of nodes within an area was to be increased.
Good day, I'm Adriel Cusi and I'm here to present SPP 2020 3D03 manuscript. The central ideas of this paper are Brownian motion and the diffusion coefficient, d. In this paper, we consider only pure Brownian motion, which is characterized by a normal distribution of displacements with a zero mean and the variance that is equal to the mean-squared displacement, MSD, where MSD is calculated using the following equation. X of t here is the probe trajectory. MSD is related to the diffusion coefficient d using the following equation. But note that this equation can be interpreted in 2 ways. First, the mean-squared displacement is the variance of the normal distribution of displacement, which gives us the following diffusion coefficient measurement, d sub var. Next, we can also consider that the diffusion coefficient is related to the mean square displacement tau graph slope, which gives us the following d sub MSD measurement. Note that dvar and dMSD gave different diffusion coefficient measurements despite coming from the same trajectories. In this slide, we also note that d sub MSD is affected by the number of fitting points used, F, and the number of MSD average displacement steps, S. This graph here shows us the dMSD measurements across the number of fitting points F at different constant numbers of S. We see that F is related to accuracy and S is related to precision, where greater F gives us more accurate measurements and greater S gives us more precise measurements. In this graph, we consider dMSD measurements in the case where we maximize S per fitting point. As we see here, as F increases, the accuracy of our measurement increases, but our precision decreases. Also note that this is the status quo for Brownian motion analysis of experimental studies. Notice the d sub var measurements represented by the dark blue color in both of these graphs. We can see that the dvar measurements are both more accurate and more precise than the dMSD measurements regardless of the F and S parameters.
The hydrophone is a common instrumentation in underwater acoustics, and it has several applications and a variety of fabrication techniques. This device is also used in underwater acoustic sensor network for offshore monitoring. This motivated our study to develop a simple hydrophone to be used for various underwater monitoring projects. We utilize a low-cost component called electret microphone to build a hydrophone. Then, in order to determine its limitations, it was acoustically characterized in water and in air. The experiment was done in a small soundproof box, and then the collection of signals was done as shown in this diagram. Both the electret hydrophone and the speaker were connected to an audio amplifier and then to an oscilloscope where we collected the signals. Furthermore, the tones were emitted from a function generator. For the characterization, we calculated the decibel values of the ratios of the signals received by the hydrophone and the signals emitted by the speaker. Then we plotted against a frequency range of 100 Hz to 100,000 Hz. Signal-to-noise ratios were also calculated to further characterize the device. Spectral responses show that the hydrophone can clearly detect signals from 520 Hz to 820 Hz in water, and 460 Hz to 1220 Hz in air. It can also detect ultrasound, but needs an enhanced amplifier. Resonance of signals were present through reflection from the boundaries, which increased the magnitude of the responses. Further characterization techniques and experiments in open water space are needed to finalize the limitations of the device. Thank you.
Neutron interactions can cause unwanted radiation exposure that pose health risks if not appropriately detected and measured. The superheated drop detector, or SDD, was one of the technologies that offer practical approach in neutron dosimetry in a mixed field both for ambient and personal monitoring. Good day, I'm Sarah Johnson, and I'll be presenting our study on the Freon-22 Carrageenan gel-based SDD. SDDs normally consist of a vial containing polymeric material with suspended liquid droplets. They detect neutrons via visible bubble formation. This formation is the result of the interaction of incident neutrons with energies imparted to the mixture. The energy transfer causes thermal agitation, vaporizing the droplets. 3 concentrations were mixed with Freon-22 in a pressure reactor. The mixtures were transferred to 10 milliliter vials, which were then placed inside the target moderator reflector assembly. The neutron source used in this study was californium-252. After 18 hours of irradiation, the vials were photographed and bubble counting was done using a cell counter. Bubble counts of post-irradiated vials rendered increasing trend with increasing concentrations and decreasing trend with increasing distance from the source. As a result of the reproducibility and sensitivity tests, only the 3% and 4% concentrations rendered reproducible results and highly sensitive response to neutron stimulation. Lastly, the linearity of the dose-response curve for the 3 and 4% indicated that the fabricated dosimeters are reliable in relatively detecting the neutron doses they received. Thank you for your attention.
Using the angular spectrum method and Fresnel transform as kernels in a modified Gerchberg-Saxton algorithm by Patricia G. Pangilinan, Dr. Giovanni A. Tapang, and Mr. Win Dunhill D. Improso. The phase information of a wavefront is crucial, but it cannot be physically measured in experiments. Phase retrieval algorithms such as the Gerchberg-Saxton algorithm, or GSA, estimate the phases needed to reconstruct the diffraction plane image using only the amplitudes. Since the GSA uses the Fourier transform as a kernel, the process of image reconstruction describes a lens system. This work explores the effect of replacing the Fourier transform kernel with free space propagation functions to simulate phase retrieval in lensless optical systems. To test the modified GSA, a circular aperture was used as the source image with a standard test image as the target. The propagation distance was varied from 1 mm to 1 meter, and the wavelength of light was set to 600 nanometers. The free space kernels used were the angular spectrum method and the Fresnel transform. Image quality was assessed using Linfoot's criteria of merit. The results shown here are the reconstructions which yielded the lowest mean square error for all the distances tested. For the angular spectrum kernel, this occurred at 639 millimeters, while for the Fresnel transform kernel it was at 635 millimeters. Both kernels yielded recognizable yet blurry reconstruction of the test image, as reflected by their high fidelity values colored in blue and relatively low structural content values colored in orange. The mean square error per iteration rapidly decreased for the first few iterations and converged eventually. The low image sharpness observed is attributed to aliasing errors in the transfer functions of both kernels, especially in large propagation distances. In summary, our paper proposes a modified GSA which uses free space propagation functions, producing image reconstructions with high similarity but low sharpness due to aliasing errors in the kernel's transfer functions. Thank you for listening.
Good day, I'm Andrea and I'm presenting our paper, Fluid Mechanics Experiments Using Commercial Off-the-Shelf Components. Addressing the need of the lack of fluid mechanics experiments, we present two setups whose parts are locally sourced and thus can be easily replicated. First, rigid body rotation, which is fluid motion in a cylinder rotating about a vertical axis. We present a simple imaging setup which 3D reconstructs the air-water interface. We have a cylindrical container on a platform with an LED light source below and an action camera overhead. Everything sits on a turntable whose rotation is controlled by a motor. The modeling method, the free surface synthetic Schlieren method, relies on the lensing effect of the surface waves on a random dot pattern under the container like so. We then record a video of the resulting waves whilst the turntable is rotating. After applying FSSS, this represents the 3D reconstructed air-water interface. Second is the experimental simulation of Philippine inter-island eddies. We simulate one of the two prevailing wind systems in the Philippines, the northeast monsoon. This setup is essentially similar to the previous one. An action camera overhead, a glass tank, a diffuser, and a light source below it. Beside the setup is a table which holds a wave maker on the upper right-hand corner to mimic the northeast monsoon. We use the two types of wave makers, an oscillating plunger and a DC fan wave maker. Philippine island model cutouts from opaque black acrylic are placed inside a glass tank. Each run covers a group of islands from the regions shown here. We scatter black pepper on the air-water surface as particle floaters. The resulting image frames for each configuration are stacked and blended to track the floater's path and displacement. This allows us to see some eddy formations. In conclusion, we were able to present replicable experimental setups that can be modified to suit other mechanical problems.
These will help enhance research on teaching fluid mechanics. Thank you.
Hi, I'm Christine. I work for Radiation Protection. Here's our work. Workers involved in ionizing radiation facilities are at risk, thus their exposure must be monitored and controlled. The survey meter is used to monitor the workplace, and it needs to work properly. That's where we come in. We calibrate survey meters to ensure that they're operational, determine the response, and optimize the overall measurement accuracy. Source field needs to be standardized, and measurements must be based on known conditions. Attenuators and collimators are used to limit the source beam to a desirable size and intensity. However, there may be changes, and this might affect the survey meter response. Thus, a proper assessment of the most effective beam must be done. Standardization of the beam was done using the following. For the response, the survey meter was placed at various distances to measure its dose rate reading. Reference air creamer rates were calculated using equation 1. Reference ambient doses were calculated using equation 2. Finally, the survey meter response is calculated using equation 3. A response closer to 1 means it's more accurate. Irradiation parameters used and measured outputs are shown in table 1. This shows the response with respect to the source to detector distance. Note that smaller source to detector distance means the closer the survey meter is to the source, the higher dose it yielded. V.1 and V.2 had the most accurate response. This may be due to its distance being at an optimal position from the source. It didn't have much radiation interactions as to when it's too close, or didn't have much scattered radiation as when it's too far. For points A.2 was closer to the source because it used attenuated beam. 8.1 had a more accurate response though. To conclude, we assessed the effects of varying cesium-137 beams to the survey meter response for radiation monitoring. At points with low reference dose, bare beam produced better response. However, it is important to note that the use of attenuators and collimators are still more practical when it comes to procedures in the SSTL. This assessment could help in developing more effective protocols for more accurate and efficient calibration services. Thank you so much for listening.
Good morning. My name is Creo Bailon, and I'll be presenting our paper entitled Pitch Control Simulation for Underwater Pipe Platform with Rise and Dive Functions. Now, we have designed a theoretical evasion system for an underwater pipe platform that's being towed by another vehicle. The basic morphology is as shown on screen. You can manipulate the volume of the air chamber to change the buoyancy of the system, causing it to rise and dive, and you can maintain horizontal orientation throughout this entire process by controlling the flow of water as shown on the right. The peculiar thing about this system is that the rise and dive functions acts as a change of system parameters for the pitch control. Now, these are the relevant torques for the pitch motion of the system. If you add them up, you have yourself a second-order differential equation describing the pitch motion of the system. Now, you have two options for the controller, either the PID or the FLC. The PID is generally more precise with the steady state, but only when it is tuned to the specific system parameters. FLC, on the other hand, adapts better to changes in system parameters, but it has natural oscillations about the steady state. The hypothesis of the paper is that FLC will perform better for damped systems because the damping will mute the natural oscillations. For the scenario shown above, we can see below how our two controllers performed. FLC generally performed a lot better since it was able to adapt, whereas PID performed a bit poorly, particularly in the dive and neutral conditions. This is of course because it is unable to adapt to the changes in system parameters. Now, this novel design has uses in evasion for underwater imaging devices, particularly those like this one with the camera below, because maintaining horizontal orientation is good for image acquisition. Thank you.
Good day, SPP. We are here to present our research about the modulation transfer function of a scanning hyperspectral imager. We are Project Optical, a project under the Stamina for Space program of DOST Pictured. One of our research and development objectives is to develop an optical payload which will be used for agricultural monitoring and disaster assessment. We have a number of teams in our project, and the airborne team is tasked with the design and calibration of an imaging system for a drone or a plane. Our design is a push-broom hyperspectral imager. It builds a 2D image by stacking series of lines across multiple shots. Here we show our optical assembly. To disperse the line, we used a prism grating prism spectrometer. Essentially, the lines in space are split into its spectral components. The result is a 3D hyperspectral cube in space and in frequency. Here we show our laboratory experiment setup. The scanning motion is approximated by the motorized rail originally designed for arc scanning. The calibration target is a series of line pair resolutions, and the reconstructed image is made from the scan. We essentially simulated a model of the scanning system and took the transects of the scan. We used sync interpolation to lessen the sampling effects in determining the proper contrast. The contrast in the experimental scans were significantly less than that of the simulation. This is due to stray light and glare not being included in the simulation model. Our results show that the MTF curve of the experimental barely reached the conventional resolution limit of 0.5 contrast. We then compared the 0.25 contrast values across the variables. Optical exposure time is always the shortest to minimize motion blur. Furthermore, slow scans prefer longer frame intervals to avoid overlaps. On the other hand, faster scans prefer shorter frame intervals to avoid undersampling. The model's ability to predict experimental behavior will help us optimize designs and parameters for anticipated scanning platforms such as drones or satellites. Thank you very much for listening, and we want to acknowledge the DOST Shirt and UPNIP for funding and implementing this research.
Greetings. I am Micah Alampay, a member of Project Optical under the Stamina for Space program. I will be presenting our paper entitled A Portable Image Scanning Platform Based on a Rotating Mirror Mechanism. We present a rotating mirror device as an alternative scanning mechanism for imaging systems. The device is portable and can adapt to a wide variety of camera setups. The main purpose of the device is to simulate the motion of drone or satellite platforms for the early stages of optical payload prototyping. The device is shown in this image. The main parts are the mirror, the stepper motor and its driver, the gearbox, and the microcontroller. The rotational speed of the mirror is derived from our anticipated airborne platform. Based on these parameters, with an exposure time of about 50 milliseconds, a rotational speed of about 0.48 degrees per second is needed for our experiments. A standard two-phase stepper motor was used for actuating the system. The minimum speed of the motor is about 55 degrees per second, meaning a speed reduction ratio of about 1:115.4 would be necessary. A custom gearbox was designed to provide the necessary speed reduction. This video clip shows an early test run of the setup in action. The camera is stationary, while the mirror rotates, producing the desired effect of the camera's view sweeping across the scene. Preliminary imaging tests were done to validate the scanning capabilities of the device. The images show the results from a 40 fps capture. Though some low amplitude vibrations were present, initial MTF measurements showed that the device is applicable for use in our experiments. In conclusion, a portable scanning mechanism for optical payload development was presented. This mechanism simplifies testing of optical payload prototypes. The applicability of the device was validated with initial MTF measurements. Thank you.